Hello everyone, welcome back. In this video, we'll be discussing about the last problem of today's weekly contest, maximum balanced subsequence sum. The problem is very interesting and a bit hard as well. If you have been following the segmentary series from some time now, we already have discussed similar problems in the past. In particular, enemy is weak and longest increasing subsequence are almost similar problems. So if you have watched those videos, I would encourage you to pause and try to give this problem a try by yourself. If you are still stuck, just watch the first few sections and then pause, and I'm very sure you will be able to crack it by yourself. If you don't know about segmentary, don't worry, I will not be assuming that you know about segmentary in this particular explanation. Though it requires segmentary at the very end, so you can just treat it as a black box at that end section only, and the entire video will still be relevant. So with that, let's get started. The problem states that you are given a zero indexed array nums. A subsequence of num is called balanced if the difference of value of the adjacent element is greater than equals to the difference of indexes itself. So let's say a subsequence contains the indexes i0, i1 all the way up to ik minus 1. For all adjacent element i0, i1, i1, i2, i2, i3 and so on, this condition should be satisfied. Now there can be multiple possible balanced subsequences. Of all balanced subsequences, we have to return the one which have the maximum possible sum of elements. So let's take an example. Let's say nums is 3, 3, 5, 6, right? One of the subsequence that is balanced is 3, 5, 6, or in other words, index 0, index 2 and index 3. Now this is balanced because every adjacent element 0, 2, you can see the difference between the indexes is 2 minus 0, 2, and the difference between the value is 5 minus 3, which is 2. So 2 is greater than equals to 2, and hence the first adjacent pair is satisfying this condition. Similarly, the second adjacent pair is 5, 6, so difference between 5, 6 is 1. Difference between their indexes is also 1, so 1 is greater than equals to 1, so this is also satisfied. So hence this subsequence is a valid balanced subsequence. Now the sum here is 14. You can try out other balanced subsequences as well. For example, 5, 6 in itself is a balanced subsequence, but because the sum of 3, 5, 6 is maximum, we have taken this and the result is 14, right? So hope the problem statement is clear. Now how to solve this? So we have this array with us and we have to figure out the largest sum balanced subsequences, and the balanced subsequence condition is every adjacent pair should satisfy this particular criteria. Now you want a subsequence, right? Your subsequence should start from somewhere, right? Either it will start from 0 or 1 or 2 or somewhere, right? Let's assume it is starting from 0. Whatever we will do for 0, we can do the same thing for each of these indexes, and the entire we can try out for all the indexes, and whichever gives us the maximum, that we will take as our answer. So but now we will start from 0, right? Now we know that our subsequence is starting from 0. What is the next element? So can 1 be the next element? The answer is yes, because 1 minus 0 is 1, which is less than equals to 6 minus 5, which is 1. So 1 is a valid possible next index. In the similar fashion, 2 is a valid possible next index as well. In the same fashion, 3 is also a valid possible next index. But 4 is not a valid possible next index. Why? Because you can see 7 minus 5 is 2, which is not greater than equals to 4 minus 0, which is 4, right? So 7 is not a valid next index. Only valid next indexes possible are 0, 1, 2 and 3, right? So from 0 you are starting a subsequence, so the starting element you have taken is the 0th element. Now the next element can either be the first element or can be the second element, or can be the third element, right? Now let's take each of this. Let's say the next element is 1 or 2. So from 0 you somehow chose that okay, the next element is 2. Now what you want from 2? You want what is the largest subsequence that will start from the 2, largest balanced subsequence that will start from the 2 having maximum sum. Isn't this problem exactly similar to the original problem? Original problem was starting from 0, give me what is the maximum, what is the largest balanced subsequence where largest is the maximum sum of the elements. Now you are saying give me the largest subsequence starting from index 2. And if you not have taken 1, if you, so we jumped from 0 to 2, right? But you can jump either 1 or 2 or 3. So if you have jumped to 1, you would have asked the same question, what is the largest subsequence starting from 1? If you would have jumped to 3 instead, or you will also ask the exact same question, what is the largest subsequence starting from index t? So hope you can see the recursion here. We have a problem which says that find me the largest subsequence starting from a particular index I. We have broken this problem down into multiple subproblems. We are saying that okay, from I you can either jump to, let's say, j1, you can either jump to j2, or you can jump to j3. So now you will simply say okay, what is the largest subsequence starting from j1? In other words, what is the maximum sum of elements of the balanced subsequence that starts from j1? You will figure out the same for j2, f of j2. You will figure out the same for j3 as well. Now you will say whichever is the maximum, that you will sum up with the value of array I, and that will be the maximum sum of the valid subsequence starting at index I, right? So hope you can see this recursion here. So let's do a dry run over the same example to make things a bit more clear. So we have this same array, we have a function f that denotes what is the that takes an index I. This will denote what is the largest, what is the maximum sum of a valid subsequence or a balanced subsequence starting from index I. Now we started at f of 0. We are saying we will first figure out what is the valid, what is the maximum sum starting from index 0, or if the subsequence starts from index 0. So we'll say from, we have already seen that from 0 we can jump to 1, or we can jump to 2, or we can jump to 3, but we can't jump to 4. Similarly we can't jump to 5 as well. So there are only 3 possible jumps from f of 0. F of either you can jump to 1, or you can jump to 2, or you can jump to 3. So from 1 you again want the same thing, what is the maximum sum of the valid subsequence starting at index 1. So from 1 again you will do the same thing, you will see where all you can jump. So can you jump to 2? The answer is yes, because 8 minus 6 is 2, which is greater than equals to 2 minus 1, which is 1. So this condition satisfied. So you can jump from 1 to 2. Similarly you can jump from 1 to 3 as well, but you can't jump from 1 to 4 because of same reason. 7 minus 6 is 1, which is not greater than equals to 4 minus 1, which is 3, right? So you can't jump to 4. So in the same fashion you will see from 1 you can jump only to 2 and 3. Now once you jump to 3, once you jump to 2, you will say where all I can jump from 2. You will see okay, you can jump to 3 only, there is no other jump possible. So now from 3 you will ask the same thing, where can I jump from 3? So there is no possible next element where you can jump from 3 because everything is smaller, right? So whatever you choose, that minus 9 would be negative, and this index will always be positive, this value will always be positive. So you can't actually jump anywhere from 9. So the answer for this is 9 itself. Basically the maximum sum you can get for a valid subsequence starting at index 3 is 9. So you will simply return 9 from here. What is the value of f of 2 now? F of 2 says that, okay, I know a maximum sum starting from index 3 is 9. So I can simply do 9 plus my current value, which is 8, right? So the maximum sum that is starting from index 2 is 17. Similarly, f of 3 we already calculated, so we will not calculate this again and say, okay, the value is 9. Now we are saying from 1, either the next element could be 2 or the next element could be 3. If the next element is 1, I will get a subsequence which sums up to 17. If the next element is 3, I will get a subsequence that sums up to 9. So obviously I will pick this one, and the value here would be 17 plus the value of current element, which is 6. So 17 plus 6 is 23, right? In the same fashion, f of 2 we already know it is 17. I am not calculating it again. F of 3 we already know it is 9. So what is the value of 0? Max of all of these plus the current value, which is 5. So the value of f of 0 is 28, right? So hope this solution makes sense. Now how would the pseudocode look like? The pseudocode is exactly what we have just discussed. We have a function f, right, which takes in an index. Now for what we will do, we'll simply, for each index, we will try out all the next possible indexes, right? We will start from index plus 1 and go all the way up to n minus 1. Now if the next index is valid, how you will check whether it is valid or not? By simply trying out this condition. So you just simply, we assume that there is a valid function which is exactly doing this thing with these two indexes, right? Now if it is not valid, we'll continue. If it is valid, it means it is a valid next index. So you can get this much sum if you jump to that index. So you will simply do max of result comma this, right? And notice we have initialized result with nums of index because we know that subsequence of length 1 is always a balanced subsequence. So the minimum sum that you will have is this itself, right? Now one more thing to note here is, you see we are getting same thing to compute again and again, right? So instead of computing everything again and again, we can simply memorize it by just saving the value of, by saving the result after the calculation, and we'll simply see if we have already calculated the result. If we have, we'll simply return that, otherwise we will go ahead and do this algorithm to calculate the final result, right? Now what is the time complexity of this entire algorithm? So one more thing to note here is, you can't put -1 here because nums is negative, so this result can also be negative at the end. So just make sure to replace it with proper, either maintain a new boolean array or replace it with some minus infinity or something, right? Now what is the time complexity? Time complexity is how many different ways to call this function multiplied by what you are doing inside each of that state. Notice that we will not compute one state more than once, so this is the overall time complexity. So how many different ways are there to call this function? N, right? Because number of distinct value of index could be n. Now what you are doing inside each function, you are iterating over the next index, and inside this we are doing some mathematical operation, right? So inside this we are doing a for loop which can run up to order n time. So overall complexity of this algorithm is order n square, which will not pass the given time constraint because the value of n is 10 to the power 5. So we have to do something better. Now we have to remove one of these n for sure, otherwise it will not fit in the given time constraint. So which of these two n you can remove? You can't remove this n for sure because you have to iterate over each index at least once, right? So this It doesn't make sense to remove this n. So we have to somehow try to remove this n. Now what this n was doing, this n was iterating over the next indexes among all valid next indexes. We took maximum value across all of them, right? So what we want to remove this n, and to remove this n we need to somehow figure out all the valid next indexes, and among all the valid next indexes we have to figure out which one has the maximum value. So two problems: first, you have to figure out valid next indexes; second, among all valid you have to figure out which one has the maximum value. So let's tackle it step by step. First, let's try to figure out what are the valid next indexes. So notice that you are now not allowed to iterate over the indexes itself, right? And without actually iterating over the indexes, you need to somehow answer that for a particular index I, let's say for index 1, what are the possible valid next indexes. So how will you do this? Notice this constraint. This constraint has, or this equation has both ij and ij minus 1 in both the sides, right? If it has both ij and ij minus 1 in both the side, no matter what you do, you have to have both the indexes to compare whether it is valid or not. You have to have this ij, you have to have this ij minus 1, otherwise you can't compare, right? But we can't afford iterating over all the next indexes. So given we are at ij minus 1, we can't afford iterating over all the ij's, and even then we need to somehow figure out all the ij's. So the clear thing is, we can't afford having both ij and ij minus 1 in the same equation, so, or in the same side of the equation. So this nice trick here is, this is a very a nice trick which we have applied many times in various contests, to mainly in prefix sums and suffix sums, to optimize the time complexity. So here what we done, we simply took ij to one side and ij minus 1 to other side, right? Now what does this do? This basically says, from this configuration, no matter what you do, if you are at ij, you need to know what ij minus 1 is to actually say whether it is valid ij or not. But now when you are at ij minus 1, you can compute this value. This value would be coming at some constant value, let's say x. Now you can say, for any ij where this value, you can compute this value of ij independently, right? For all of the indexes you can compute this. Now for any ij, if the value is greater than equals to x, then that is a valid ij for the current ij minus 1, right? So let's take an example. Let's say this is the given array, right? Now as we discussed, we have to now do comparison on based of nums ij minus ij and nums ij minus 1 minus ij minus 1. In other words, we have to do comparison on this kind of array where we have just subtracted the corresponding index with the number 5 minus 0 5, 6 minus 1 sorry 5, 8 minus 2 6, 9 minus 3 6, and so on and so forth. Now let's say this is the current index ij minus 1. So what are the possible ij's? Possible ij's will be the value where the value in this array is greater than equals to 6. So this is a possible ij, and there is no other possible ij at all, right? So for 2, only valid next index is 3, right? In the same fashion, let's say you have to figure out what is the valid next index for 0, right? So you looked at this array for 0, the value here is 5. So everything which is greater than 5 in this array are the valid next indexes for 0. So here 1, 2 and 3 are greater than 5, greater than or equals to 5. So the valid next index for 0 is 1, 2 and 3. No other indexes will be valid index, or will the valid next index for the index 0. So hope this entire thing makes sense. Now notice we had two problems. First, we need to figure out the valid indexes. Second, we have to figure out the maximum across all such valid indexes. So we now can figure out valid indexes without iterating over all the next indexes. So that problem is solved. Now we want maximum across all the valid indexes. So if you keep your array like this, you can't actually do a range query here, right? So you want maximum across a range in less than order n time. So you need to do some kind of range query, right? So what you can simply do, you can simply sort this array, and in the sorted array, taking the valid next indexes would be a range, and you can simply take that range and query in that range. So let's take an example. Let's say we had this array initially, we converted this array to something like this based on the equation that we have seen. Now we want all the indexes, all the valid indexes in a particular range L to R, because if it is not in this range, you can't do range query. You want maximum, right? You want maximum across all such indexes. So you have to do, to actually get this maximum in less than order n time, you need to do some range, you need to use some kind of range query data structure. In other words, you want all the indexes which have the value, which have the valid value in a particular range, valid value for a particular index, to be lie in a range L to R. So for 0, you want to query some range L to R. Similarly for 4 you need to query some range from L to R. You can't say, okay, for 4 I know that everything greater than 3 is correct value. So you can't say this is correct, this is all correct, so I will query this and then I will query this. If you do this, you have to iterate over all of them again. You don't want to iterate all of them. That's why you have done this work of figuring out what are the valid indexes. So what you will do, you will simply sort this array, right? Now everything which is a valid index lies in one side of the array. So let's say for 0, you want all the valid indexes for 0. So you will simply look where this 0 lies in this sorted array. 0 lies here. So all of the indexes after this are valid indexes for 0. So you will simply do a range query across the values of this indexes, right? Not this 566. Instead, what will be the value of f of 1, f of 2 and f of 3, right? So you will do range query over this, right? Now one important thing, this is not always true. Why? Because let's look at this 4 for example, or maybe 9 for example, right? So if you look at index 9, you want to know what are the next indexes. So there is no next index at all for index 9, but here you have -7. So you will say all these indexes are valid next indexes, but it is not true because there is nothing after 9 exist. So you, along with this value thing, you also need to take care of the fact that you are only considering the indexes which are greater than the current index itself. So this problem is something we have exactly solved in multiple different problems before. Enemies is weak is something where I introduced this concept for the first time, and longest increasing subsequence has exactly this concept. So if you have watched any of these video, I would strongly encourage you to pause and try to solve the problem from here onwards by yourself. So hope you have at least tried it. Now what we want two things. First, all the indexes in the right should be valid, right? That's what we want. Second, we also want to only take care of those indexes which lies after the current index. So we only want to take into consideration only the indexes or only the values which are greater than 9, not anything less than 9. So that for that, what you can do, you can simply maintain a mapping. So you want all the values greater than 9, or all the values greater than 9, which means you want you are sure that everything here are valid, right? But you also want indexes which are after 9, right? So what you will say, I will start from the back, and initially everything will be inactive. So every of these index is inactive. This is inactive, this is inactive, this is inactive, and everything is inactive. In other words, everything is 0, let's say, right? So f of 3 is 0, f of 2 is 0, and so on and so forth. Now whenever you fix, or whenever you have taken something, you will simply activate that index. So if you have figured out the value of 9, you will simply put the value of 9, and this means this index is now activated, right? In the same fashion, if you are, let's say, at 6, you figure out, you continue your journey, you reach 6, so you already have taken care of 7 and 8. So in other words, these indexes are also activated. Now you are coming to 6, so 6 lies here, right? So let's just get rid of these things. So 6 lies here. Now you want all the valid indexes for 6. You know that all the valid indexes lies in the right. So there are so many indexes, but only the index which actually lies after 6 will be activated. No one else will be activated. So you can simply do a range query over this range, and you will be sure that only the index which is activated will be taken into consideration. None of the other index will be taken into consideration, right? Just to reiterate this part, we had two problems. First, we want a range for a range where everything after a particular index is valid. So that we have done by sorting this array. But now once we have sorted the array, the index is lost, the index ordering is lost. So to keep the index ordering with us, what we have said is we will start our journey from right to left, and initially everything will be inactive. We will keep on activating the elements as and when we go right, and because we are activating the element in its correct mapped position, the first condition still holds. Basically everything after a particular index will be valid, but only the index which lies after me will be activated. None of the others will be activated, and hence if we do the range query, we will get the correct value. So that's the crux. Let's do a small dry run over a couple of elements, and then we will look at the pseudocode finally. So let's just get rid of this. We have these things now. Initially everything is 0, so we start at 9 mapped to this thing. In other words, everything after this is a possible valid candidate for 9 for the next element. So what we will do, we will do a range query, range maximum query, for finding out the maximum in this range. So everything is inactive, in other words everything is 0, so you will get maximum as 0. So the value of index 9, or the maximum sum of a valid subsequence starting at index 9, would be 2 plus the maximum, which is 0, right? So the value of f of 9 is simply 2, right? So once we have figured out the value of f of 9, we will simply put this value here. In other words, this is now activated. Now we go to find the value of f of 8. F of 8, again go to the corresponding mapped index. Everything after this is a possible valid candidate. Now we want to only consider the elements which are actually after 8, and that will be taken care by the fact that we have only activated those elements which are actually after 8. So we will simply, everything else is a neutralized value, right? So either 0 or minus infinity, your wish. So here the maximum in this range is 2, right? So what you will simply do, you will simply say the maximum is maximum in this range is 2. In other words, wherever I can jump to, so from f of 8, let's say you jump to couple of indexes, right? Maximum across all of them is 2. So what is the value of f of 8? 2 plus whatever is the value at index 8, which is 4. So the value of f of 8 is 6, right? So we'll simply put 6, we'll simply put 6 here, right? Now let's find the value of f of 7. Again 7 mapped to this, so everything after this is valid or possible valid candidate. We'll simply do a range query. It will give you range maximum query. The maximum in this range is 0. So the value here is 7 plus 0, which is 7. So 7 here, right? So let's do a few more. 6 mapped to this. Again everything after this is valid, but you only have to consider the elements which are actually after this. So for that, if you do the range query, it will automatically taken care of because only those elements will be activated till now. So if you do the range query, the value would be coming as 7. In other words, from f of 6, if you jump to all possible values you can, the maximum across all of them is 7. So the value of f6 would be 7 plus 6, which is 13. So the value here would simply be 13, right? Now in the same fashion you will continue, and after some time you will be having all the values for all the indexes. So you will have value of f of 8, f of 9, f of 6, f of 7, and so on and so forth. Now remember, we can start our subsequence from any of these indexes. So once you have filled this entire array, you will simply take maximum in this array, and that will be your final answer, right? So what is the time complexity of this entire algorithm? Time complexity, what we are doing, so let's first look at the pseudocode and then we will derive the time complexity from that. It will be easier. So the pseudocode will look something like this. So what we are doing, we are first trying to get this array and then sort this array to get the actual mapping of the position in the sorted array. So that's what we have done. We simply maintain this array along with the indexes, right? We sort that, and once you have sorted this, you maintain where does a particular index I will map to. So you want to know where this 7 lies in this sorted array. Similarly, you want to know where this 6 lies in the sorted array. So that's where you computed this particular map, and that will help you with this mapping itself. Now after that, as we have discussed, we'll start our journey from right to left. So we'll start from n-1, go all the way up to 0. For each index, we already know where it is mapped to. So we already know that position. Now everything after POS is a valid candidate, but we only have updated, or we only have activated the elements which we actually have traversed. So we only have activated the elements which are lying in the right of the current element. So we can simply do a range query in this range position to n-1, and this will give us what is the maximum across all the valid candidates. Again, there can be, so if you look at 6, there can be multiple valid candidates, right? but you are only interested in those which actually lies in the right. So you are only interested in 7, not anything else, and this is already taken care of because this only 7 will be activated because you are only activating the elements starting from the right. So if you do this, you will get what is the maximum element or maximum value over all the indexes in the right. So we'll simply do array I plus that, and finally you will update the value at current position as well, so that the next set of elements can take the advantage of that. So in other words, you are activating this particular position in this array, so that if an element that lies in the left comes, this element will be taken into consideration, right? Now what is the overall time complexity? We are sorting an array here, so this will take order n log n time, and then we are maintaining this map, so we can use unordered map here, so that will just take order and time. After this we are doing a loop, so n number of times we are doing something. What we are doing, we are finding out the position. Again, if you use unordered map, that will be order 1 operation. You are querying a range in the segment tree. In other words, you want this operation to be login, and hence you will simply do range maximum query, so that will just take you login time. And finally you are updating a particular position in the segment tree, that will also take you login time. So in total you are doing n log n plus n log n operation across all of these, and the complexity of this entire algorithm would hence be n log n, which will pass the given time constraint. So if you have watched till this point, I would strongly encourage you to pause and try to code this entire thing by yourself. If you are not able to code this, feel free to rewind the video and watch the particular section where you feel you are missing something. Once you have tried this out, you can try out these problems: enemy is weak, longest in subsequence, and I think there is one more in between that. So you can try out these problems. All of these is there in, it will be in the description down below. You can check them out, and it is also there in the Google Doc, which has a short link of bit.ly/segment-trees. So hope you have at least tried this once. So let's look at the code now. This is a segment tree code. Will not, if you not know what segment tree is, there's already a series, all the videos are there, you can watch this. For now you can simply use this as a black box, which have 3 functions: update a particular index and query a maximum in a particular range. You can treat this as a black box, copy paste this and use it in your actual code. Now what we are doing, as we discussed, we will simply figure out what is the correct mapping of the indexes. So for that we prepare a value and index array, we sort that, and then we prepare the actual mapping. After that we go from right to left, n-1 to 0, because we only want to activate those elements which are actually in the right. So we figure out the index, we did the query and added nums of j, that will be the value of the current value of f of j, right? Once we figure out the value of f of j, we'll simply update it in the segment tree, so that next elements in the left can take the advantage of it. Once we have this, we'll simply return the maximum across all of the indexes from 0 to n-1. So hope you understand this entire problem. If you have any doubts in any of these, feel free to follow up in the comment section below. I would be happy to answer. If you like the video, give it a thumbs up and do subscribe if you haven't already, and I will see you in the next one. Thank you.